Hello universe, today we're going to be solving problem 2 of Baby Rudin, which asks us to show or to prove that there is no rational number whose square is 12. Okay, so to do this proof we're going to use a method called proof by contradiction because we want to start with something we can kind of get our hands on. So if I begin the proof by supposing, for sake of contradiction, that there is a rational number whose square is 12. So there exists a rational number, so R within the rational numbers such that R squared is equal to 12. Okay? So now we have something to work with. We have this number R. Okay? And okay, so since R is a rational number, there exist some integers R1 and R2 with, these are integers with R equals to R1 over R2. Okay? By the definition of being a rational number. So now I have that R squared is equal to R1 squared over R2 squared is equal to 12. So if I multiply both sides of this equation by R2 squared, this is going to tell me that R1 squared is equal to 12 times R2 squared, okay? And now we're going to need to look at the number 12 and analyze why this equation cannot happen. So what we want to do is look at the prime factorization of the number 12. It's a famous theorem by Euclid which states that every integer has a unique prime factorization. So it can be uniquely written as a product of prime numbers. This unique product of prime numbers is essentially like the fingerprint of a number, okay? So let's just recall that 12, prime factorization of 12 is 2 squared, which is 4, times 3, okay? Is unique prime factorization of 12. Okay? I made a video proving that there is such a unique prime factorization. This is also a very famous proof by Euclid. So you should attempt the proof by yourself. If you haven't seen the proof, try to prove the statement that every natural number, every integer, has a unique prime factorization. Okay? This is a really great exercise to try and prove that claim. And there are various resources available online. I've made some videos, as well as many other people probably have made videos on this idea. Okay? But let's see how it applies to our setting here. So we have that that R1 squared is equal to 2 squared times 3 times R2 squared, okay? So notice that that the power 3 is to an odd power in this expression, okay? And any factors of 3 that divide R2 are going to be raised to the, so let's say that, let's just say that 3 to some power, let's say 3 to the k, divides R2, then R2 squared basically contains a factor of 3 to the 2k. So I should be a little bit more clear about this. But the idea is that if I compare the powers of 3 is a prime number, okay? If I look at the powers of 3 on the left-hand side, they must be even because r1 is raised to the second power. The powers of 3 on the right-hand side must be odd because r2 is raised to the second power. Okay, so in particular, the left and right-hand sides must have different prime factorizations. Since 3 appears an even number of times on the left-hand side and an odd number of times on the right-hand side. Okay? So this is the intuitive reason. I'm not going to write it out because I just explained it. 3 appears an even amount of times on this side because we have r1 raised to the second power. So this 2, any factors of 3 that belong to r1 are going to get multiplied by 2 in their exponent. So the powers of 3 that show up in the left-hand side, 3 must be raised to an even power. On the other hand, on the right-hand side, this r2 squared, any multiple of 3 that goes into r2, when it's squared, I'm going to have an even amount of 3's. And then finally, I have this multiplied by a 3 to the power 1. So I'm going to end up with an odd amount of 3's on the right-hand side. So basically, we have one number with 2 different prime factorizations, which contradicts the uniqueness of a prime factorization. So this is the fundamental reason why this statement must be true. Okay, and this logic will extend to much more numbers than just the number 12. But what I'm going to do is I'm going to go through the way that you're probably used to seeing this proved if you look at the square root of 2. So doing it a little bit more rigorously, or like this could be unpacked very rigorously and made into a very rigorous proof, but I'm going to go along the route of kind of the introductory level, which the proof style that you often see in these classes. So let me just do that real quick. Okay. So again, this backs our intuition, and we could make what I just wrote and erased much more rigorous. But let's try to do it in a slightly different way. Okay. So we just look at this expression and we recognize that 3 divides r1 squared. Okay. So this tells me that 3 must divide r1 since 3 is prime. Okay. So yeah, 3 dividing r1. If 3 divides ab, then 3 divides a or 3 divides b. Okay, so recall that 3 dividing ab implies 3 divides a or 3 divides b. So in this case, 3 divides r times r. So 3 divides r or 3 divides r. So in either case, 3 is guaranteed to divide r1 here. Okay. So I was saying r earlier, I meant r1. So 3 divides r1 times r1. Therefore, 3 must divide r1 or 3 must divide r1. So in either case, 3 divides r1. And so therefore, 9 must divide r1 squared. Okay? So if 3 divides r1, then r1 squared will have 2 powers, or at least 2 factors of 3 in it, right? So 9 divides r1 squared. This is because, right, like one of the 3's, so if I write r1 as 3k and 3k, then I can see I have 2 factors of 3 now. So I have a 9 that divides r1 squared. And so this tells me that I can factor out a 3. So I can write this expression as, let's say I write r1 okay, so let's let R1 equal to 3 times K1, because I know 3 divides on 1. So then I must have that, if I replace this expression with 3 times K1, then I'm going to have 9 K1 squared is equal to 2 squared times 3 times R2 squared. And then I can factor out a 3. I can cancel a 3 on both sides. So I get, dividing by 3, I get 3 here, and this 3 cancels. Okay? So I get 3 divides 2 squared times R2 squared. So let's write that up here. So therefore, 3 divides 4 R2 squared. So this tells me since 3 is prime again, 3 divides 4 or 3 divides R2 squared. This is obviously false. So 3 divides R2 squared. This means that 3 divides R2 by the same logic that we discussed previously. So 3 divides R1 and 3 divides R2, okay? This means that R within the rational numbers cannot be written in simplified form. Right? Because I started with an arbitrary, basically the way that this proof just worked is we had R as R1 divided by R2, which is arbitrary, which is an arbitrary representation of R and Q, okay? So these two integers were arbitrary, and then we showed that 3 divides R1 and 3 divides R2 if we assumed that R squared is 12. So if we assume that R squared is 12, then we showed that 3 divides R1 and 3 divides R2, which means that that this expression, no matter what I choose for R1 and R2, I can keep canceling out of 3. And then I'm going to basically run out of factors of 3 to keep canceling out. So this contradicts the ability to write R in simplified form Okay, so let's just go a little bit more in detail here. So why can we always write a fraction in simplified form? So in particular, so if we want to be more specific about this, then given R1 and R2 in the integers, okay, 3 to the n divides R1, let's say 3 to the n1, and 3 to the n2 divides R2 for some n1, n2 maximum, okay? So essentially, n1 is defined to be the supremum of the set of integers such that, or positive integers, non-negative integers, such that 3 to the k divides, I should use a colon for my such that symbol, such that 3 to the k divides R1, okay? And notice that this set must be bounded because 3 to the k approaches infinity. So eventually, 3 to the k, you can show by induction, is going to approach infinity. And therefore, this set, right, once 3 to the k exceeds the value of R1, then, of course, no k greater than that can ever satisfy 3 to the k divides R1, because 3 to the k will literally be larger than the number R1. So this set is bounded above. It's also bounded below by 0. Therefore, this supremum is actually realized. And so this is a well-defined number, n1 here. And it's basically the largest power of 3 that divides R1. So this is the amount of factors of 3 that belong to the number, the integer R1, okay? And essentially, what we can do is write, what this means is that, let me write it over here. Means is that R1 over R2 is going to be 3 to the n1, let's say, times k1. Again, I'm kind of abusing notation. Now I'm writing R1 as 3 to the n1 times k1 over 3 to the n2 times k2. So, and then so I'm defining k1 to be R1 divided by 3 to the n1, okay? This is an integer, because 3 to the n1 divides R1. So now I have this ratio, and now I can cancel out the factors of 3 as necessary, and I'm going to get, notice that 3 does not divide k1, essentially, because otherwise that would contradict the maximality of n1, right? If 3 divides k1, then 3 to the n1 plus 1 would divide r1, just a contradiction. So k1 is not divisible by 3, similarly k2 is not divisible by 3, and so I can cancel these factors of 3 out inductively. So let's just say this is 3 to the n1 minus n2 is k1 or k2, and the idea here is that, okay, if this number 3 to the n1 minus n2 is going to be positive if n1 is greater than n2. Of course, it'll be negative if n2 is greater than n1. Okay, so we could consider this to be two separate cases, but in either case, we know that one of either the numerator or the denominator is not divisible by 3. Okay, so let's just look at case 1 here. Case 2 is identical. So case 1 is if n1 is greater than n2, greater than or equal to, in which case we have written basically r1 over r2 in a form which is like 3 to some power, literally n1 minus n2, times k1 over k2. But k2 is not divisible by 3. We just showed that for an arbitrary representation, I must have that both these are divisible by 3. So that's a contradiction, right? This tells me that k2, by my proof that we already gave, k2 is divisible by 3, which is a contradiction. Okay? So this was maybe a bit more in detail, kind of went over a lot of different techniques here, but we kind of proved essentially one way that you could realize the fact that every fraction has a simplified form, and once you ensure that every fraction has a simplified form, then the prime factors, okay, none of these R1 and R2 can share any prime factors, okay? So simplified form means if you assume that every number has unique prime decomposition, which is really the heart of this proof, and if you assume that from the very beginning, you can really just solve the proof almost instantly. Not almost instantly, but it's a lot easier with that piece of information. And then the idea is that R1 and R2 have these unique prime decompositions, and then those prime decompositions, those prime factorizations are finite, and so, because these are finite numbers, and so we can cancel any common factors in the prime decompositions, and that will leave us with the simplified form. The simplified form is going to be R1 and R2 share no common prime factors, okay? And if we ensure that R1 and R2 share no common prime factors, then in particular, of course, 3 cannot divide both R1 and R2, right? Because, because 3 is a prime number, so it can't belong to both the numerator and the denominator if we're in what's called a simplified form, okay? And then you could generalize this proof idea to any number which has some sort of odd, some sort of prime. If you look at its prime factorization, if any of the primes in its prime factorization is raised to an odd power, then this proof technique will still work, okay? So we could change the statement we could change the proof using the same exact strategy. There is no rational number whose square is, let's say, is equal to n, where n, if we take the prime factorization of n, let's call this p1 times to the power k1, p m to the power km. This is the prime factorization. Which again is guaranteed to exist for any natural number and is unique, where at least one of these k1 through km's is an odd number. Okay? So we can just look at how we proved the problem and generalize it to this much more general form. And then again, we want to prove this using the lemma that every integer has a unique prime factorization. Okay, so now I'm going to challenge the viewer to prove this lemma. If you have not done so, or if you haven't seen a proof. If you have seen a proof, try to remember how it's done, and then you can look it up or review it on your own. Okay, and I also have some videos on this lemma from a while ago. But then try to prove this more general statement. Okay, so once you have the lemma, try to prove the more general statement. Again, I kind of did all the work because I didn't do all the work because you're going to have to get, if you're not familiar with proof writing, you're maybe going to have to deal with all these indices floating around and trying to make the language rigorous. But I already gave you the key idea, which is you basically write the fraction in simplified form. It doesn't even have to be in simplified form, actually. This is the power of this proof strategy, is that, remember, we literally just had, just state it real quick. So for the number 12, recall, we looked at R1 squared is equal to 12 times R2 squared. Then I took the prime factorizations, and I had 2 squared times 3 times R2 squared. And then I identified that this side of the expression has an odd number of 3's in its prime factorization, and this side had an even number of 3's in its prime factorization, okay? And that contradicts the uniqueness of the prime factorizations, because these are two different prime factorizations of the same number. which is impossible because these prime factorizations must be unique. So I want you to generalize this idea to a integer n, which has a prime factorization such that one of these powers in its prime factorizations is an odd number. Okay? All right, and the idea should be pretty much following this exact logic, but writing it out, if you're new to the subject, writing it out is a good exercise in just proofwriting structure in general. Okay? All right, thank you.